Okay, so we're going to do another problem here where we use the definition of the derivative to show that another function is not differentiable at x equals 0. And this is a piecewise defined function. So particularly when you're looking at a piecewise defined function at the place where the domain changes for the different types of functions you're going to use for the different pieces, this is how you'd want to show that a function is or is not differentiable. All right, so we're going to start with the definition here. So we're going to say the derivative at 0, and since we're supposed to be showing this at 0, I'm going to put 0 in for x on our definition here. Limit as h approaches 0, f of 0 plus h minus f of 0 all over h. Okay, so the important thing about this function is that when I put in x equals 0, I'm using one piece of the piecewise defined function. And then when I put in values for the input that are not 0, I'm using a different piece for the piecewise defined function. So for these two function expressions here in the numerator, I'm going to be using the two different pieces of the piecewise defined function. The other thing I might do as I do this, just to make my work a little simpler, is to notice that 0 plus h is just h. And so when I put that expression into the correct piece of the piecewise defined function, I'm just going to write h. So we've got the limit as h approaches 0. And here we're putting in something that is not 0. So we're going to put that into the first piece of the piecewise defined function. And so I'm putting in h. And then f of 0, I'm using the second piece of the piecewise defined function. And so I have this. All right, so now I want to evaluate this limit. So I might notice, first of all, there's a little bit of simplification I can do here. Minus 0 on the numerator, so that term goes away. I can just rewrite the numerator as h times sine of 1 over h. And then I have these h's here that I can cancel and simplify. So I end up with the limit as h approaches 0 of sine of 1 over h. Okay, and so we can't use a substitution shortcut to evaluate this limit because obviously I can't put in h equals 0 to the denominator here. So I need to think a little bit about what's happening here. All right, so as h approaches 0, this expression inside the sine function, as h approaches 0, this expression here will approach different things on either side of h equals 0. So let's consider first of all what happens when h approaches 0 from the right. So let's first of all think about what happens here when I let h approach 0 from the right. All right, so as h approaches 0 from the right, this expression inside will approach positive infinity. So this expression inside here will approach positive infinity. And so I want to think about the outputs of the sine function as that expression inside the sine function approaches infinity. We know that the sine function is bounded between -1 and +1, and it'll take on all output values between -1 and +1 as that input goes to infinity. So this limit right here does not exist because the function does not approach a specific output value as this input part approaches infinity. It also doesn't go to infinity or positive infinity. So this limit does not exist. Similarly, when I let h approach 0 from the left, I will also show that this limit does not exist, but I don't really need to do that because at this point I've already showed that this limit does not exist. And so this is the definition of the derivative whenever this limit exists. And because our limit does not exist, we've shown that this function is not differentiable at x equals 0.